Hey, it's a great day for calculus. Problem number 1. At time t greater than or equal to 0, a particle moving in the xy plane has position vector given by s of t equals 4t comma t cubed. What is the velocity vector of the particle at time t equals 1? So I'm given a position vector. That would be a vector function. And I need to find the velocity vector. And so the derivative of position is velocity. So my velocity vector function is going to be just the derivative of each component here. I'll take the derivative of 4t, which is 4. I'll take the derivative of t cubed, which is 3t squared. And there's my velocity vector function. Now I need a particular vector at time 1, and so the velocity vector at time 1 is going to be 4, 3. There we go. Problem number 2. What is the slope of the line tangent to the graph of y squared equals 3x plus y equals, what I say, y squared plus 3xy equals 4? At the point 0, 2, slope of the line tangent to the graph. So I am going to go ahead and take the derivative. This will be implicit differentiation. Slope would be dy dx. And so anytime I have an x in here and I take its derivative, I don't need to write x prime. That equals 1. But if I have a different variable like y, I am going to need y prime to be there. So I'll start by just taking the derivative of each term. The derivative of y squared with respect to x is 2y, y prime. The derivative of 3xy is going to take a little bit of product rule. So I'll take first times derivative of the second plus second times derivative of the first and the derivative of 4 is 0. Now I need to solve for y prime. Let's subtract 3y from both sides. Factor out a y prime. Solve for y prime, negative 3y over 2y plus 3x. And now I'll go ahead and evaluate at this point 0, 2. Plugging in 0 for x, that goes away. Plugging in 2 for y, I get negative 6 over 4 plus 0, which I can reduce to negative 3/2. There we go. Looks like B. There we have it. Number 3. Find the area of the region between the curve y equals 4 to the negative x and the x-axis on the interval 1 to infinity. Now that's interesting. Looks like we have an infinite region. 4 to the negative x. It's going to look kind of like this. We're interested in the area of the region between the curve and the x-axis on 1 to infinity. It's going to keep on going forever. Possible that it turns out to be a finite value. We'll see. I guess my only options are finite values, so I'm assuming that's going to happen. I'm not going to write this all out with limits, so this is a little bit shortcut here. The way that I'm writing this, if this were a free response, I would create a proper integral out of this, but I'm going to go ahead and leave it improper and work with it. and I'm going to be able to come up with my value that I need just fine. So this is an antiderivative that does need some thinking here. If you think about the derivative rule, right? What's the derivative of a to the u? A little easier when it's e, but it's not e this time. So the derivative of e to the u would be itself, of a to the u, sorry. Derivative of a to the u is itself times the natural log of a, and then chain rule says times derivative of u. I'll squeeze that in maybe with a u prime. So those three pieces, if I wanted to reverse this and go backwards, right, what is the antiderivative of a to the u? It is itself. Now I'm going to divide by the natural log of a, and I'm going to divide by the derivative of u. That's the antiderivative rule. That's a good one to know. You should know that. That's probably the hardest of your antiderivatives that you'll do without using substitution or parts. So I'm going to go back here. My antiderivative is itself divided by the natural log of a divided by the derivative of the inside, which would be -1. So I'm going to do that just by making this negative here. And then I think I'll rewrite this one more time before I evaluate. I have a 4 to the negative x here. That would be the same as 1 over 4 to the x. So there's my negative. 1 over 4 to the x is the same as 4 to the negative x. And then continuing my denominator here, I've got a natural log of 4. And now I'm ready to evaluate from 1 to infinity. This would be the point. If I was using, if this was a free response, I would be using limits at this point, writing out limits and all that. But I can just think through what would be going on in limits since this is a multiple choice, and I'll be able to come up with the answer just fine. So I'm plugging in infinity to start with. That is going to become 0 right there. 4 to the infinity gives me infinity in the denominator times natural log of 4, still infinity in the denominator. So I've got 0. Now I'm going to subtract -1 over 4 to the 1 natural log of 4. So I got this double negative here. I'll just go ahead and call that positive. I've got 0 plus 1 over 4 natural log of 4. There we go. That's one of my options. All right, final question. Number 4. The region enclosed by y equals the square root of x and x squared is rotated about the line y equals 5 to create a three-dimensional solid. Find an equation for the volume of the solid. I am going to go ahead and sketch this just so I can get a visual on what's going on here. The curve y equals the square root of x looks like this. Square root of, or let's see, x squared goes like this. And so I've got my region right there. This region is rotated around the line y equals 5. 5. So there's the center of this thing. We're rotating around that. And so I'm going to put the mirror image of this. In order to draw this, I'm gonna put it up here. Look a little bit like this. And this thing is rotating around, so I'm going to give it a little three-dimensional quality here. That's what my three-dimensional solid looks like. So if I were to slice this thing to get a cross section, my cross section is going to be a circle with another circle inside of it, a hole. Both of those circles are changing as you change the x value there. If I can find the area of this cross section, then I'm good to go. So I have a large radius and I have a small radius. I'm going to find the area of the big circle and the area of the small circle. The large radius would extend from the center of this thing, that's right here. I'm actually going to draw it downward like this, to this curve, which is x squared. So to get that length, I'm going to take 5, which it would be from here to here, would be 5. I'm going to subtract from that this distance, and I'll be left with this distance right here. So the large radius equals 5 minus x squared. The small radius is going to extend from the center down to the top curve. So that distance is 5 minus the square root of x. And now I have the radii. I can come up with a formula for area of a cross section. The area is going to be big circle, pi, big radius, squared, minus little circle, pi, little radius, squared. That's the area of a cross section. To turn that into volume, you simply you take the integral of the area of a cross section, 5 minus x squared, squared minus pi, 5 minus square root of x squared. It's still area at this point until I give it another dimension, and that's this right here. That dx is going to give it a depth now, and all of a sudden we're finding volume. Where do I start? Where do I end? First cross section is here at x value of 0. Last cross section is here at an x value of 1. Boom, there we go. You can factor that pi out and bring it out front, which is what we see in all of our options here, so that's what's going to happen there. We want 5 minus x squared coming first, and we want to go from 0 to 1. So it looks like letter C is going to be my option here. Okay, there's 4 problems that are similar to your mini test coming up.